Hello again, everyone. Welcome to our discussion of section 1.2. Today we'll be mainly talking about properties of exponent and properties of radical expressions. And then these two properties will be very important in simplifying expressions. But before that, I want to remind you about something that I mentioned at the beginning of the first video lesson, which was how to study this subject. Is first, you would want to skim through a textbook section or topic before it is covered. So I hope you've done that. I hope you've already gone through the textbook in section 1.2 and just read through it. It doesn't matter if it all makes any sense to you at this point, but that read through the section once before it is covered, either in this video or in class. You shouldn't take more than an hour to do it, preferably sometime about 45 minutes, depending on the length of the section. I'd say somewhere between half an hour to an hour would be an optimum duration for skimming through a section. And second, attend each class and take notes. That would be useful to you. And this would be good because when you show up in class, then your other friends, if they have any questions, you get to listen to those and hear them. Those questions might be relevant to the questions that you have. And also review your lecture notes and solve all problems your teacher solved in class without looking at the solutions. That's number 3. So after you take the notes in class or after you watch this video, and when I post any of these notes on Canvas, when you get to these examples, even the examples that you see in the book, before you look at the solution, either in lecture notes or in the textbook, solve those problems on your own before looking at the solutions. Okay? And complete all homework assignments by the due date. These are designed and timed so that you perform your best on exams. So if you postpone them and if you have a valid reason, yes, I would be willing to extend the due dates, but if you're completing too many homeworks beyond the due date, then you're probably not as prepared as you should be for the exams. And of course, lastly, review. Okay, having said that, let's talk about this section 1.2. First of all, we have properties of exponent or properties of powers. These are extremely important. Anything to 0 power is 1. Anything to negative power can be rewritten as that same thing with a positive power. So for example, if you have, because we quite often, not in every single case in mathematics, but quite often we would like to write negative powers in terms of positive powers. So if you have, as an example, if you have, say, 5 to minus 1 power, you can rewrite that as 1 over 5. If you have, by the same token, if you have, say, 4 to negative 3 power, you can rewrite that as 1 over 4 cubed. Or if you have something like this, 1 over 4 to negative 3 power. If the negative power is in the denominator, you can bring it up and make it positive. So 4, when you bring it to the numerator, it gets multiplied by a negative 1. So minus 3 or 4 cubed. So 1 over 4 to negative 3 power is equal to 4 cubed. If you have two terms that are being multiplied, if the bases are the same thing but the powers are different, then the powers get added. What we mean by this, suppose, for example, if you have 2 squared times 2 cubed, right? The bases are the same, so we can add the powers, 2 to the 5th power, or 32. Okay? If you have a fraction like this, such that the terms in the numerator and the denominator have the same base but different powers, then you can subtract the powers. This is helpful because you want to combine the two terms into one because they have the same base. So for example, if you have something like, let me choose an easy base like 2, say 3 say to the 5th divided by 3 over -1. So what will happen? We can subtract these, just like this formula is saying. 3 to the 5th minus -1. So 3 to 5 plus 1 power, or 3 to the 6th power. And we can find out what that is using a calculator. So we have 3 to 6th power, and that would be 729. Okay. Just like the properties we discussed in section 1.1, when you look at these properties, think of them visually. Try to see what visual patterns exist in these properties. These properties are highly visual. Okay. So if you have some base a to some power inside of a parenthesis that is being raised yet to another power, n, then you can multiply the power on the outside by the power on the inside. Okay, and that would be the power of the whole thing. So as an example, if you have, say, 3 squared to 4th power, then multiply those, we get 3 to the 8th power. Okay, and what is that value? We can calculate it, which is 6,561. Okay, if you have two terms that are being multiplied, raised to a power, you can distribute the power on the outside to each term on the inside of the parentheses. So a to the n power times b to the n power. This is true only and only if you either have a multiplication operation or a division operation. If you have subtraction or addition, please, I've seen that many times. That does not, this rule, these two rules, do only apply to terms that are being multiplied and divided. They do not apply to terms that are being subtracted or added. So for example, can you say a plus b to n power equals a to the n plus b to the n? Can you do that? No, because these two terms are being added. The same thing is for the subtraction. Okay, so those two rules apply only when the terms on the inside are being multiplied or divided. Okay. If you have a fraction raised to a negative power, you can write the same fraction to positive power by flipping the terms on the inside. So if you have, for example, if you have 3/4 to minus 2 power, you can simply say 4/3 squared. Just by flipping the terms on the inside, you can make the power on the outside positive. Okay. Here, if you have a fraction such that the numerator and denominator have negative powers, you can make those powers positive by simply moving them around the fraction. I mean, all of these rules are so important, and especially some of these, especially that one. So what that rule is really saying, let me use a scratch paper to make sure that everyone understands what that is saying. That rule is saying this. Suppose if you have, say, 5 to minus 2 power over 4 to minus 6 power. So that is equal to, you can move things around. You can bring this down, and I'm going to start with something really easy. So you see, and I'll give more examples on this. So then you can move this up and make the power positive. You can bring that down and make the power positive. Okay? But that's true for any term. So suppose if we have something like this, 3 negative to negative 2 power, y to negative 4x over z negative 2 and then m, say 7, right? So anything with a negative power you can easily make positive by moving it around. If it's in the numerator, you can bring it down. So 3 to negative 2, you can put it here and make the power positive. Bring it down. And these are not, because these are being multiplied. Again, guys, we can do this because everything here is being multiplied, and we are dividing or multiplying things. If you had addition and subtraction, you could not do this. Okay? So the z to minus 2 power, I can move it up and make the power positive. The y to negative 4 power, I can move it down and make the power positive. X is happy because it's got a positive 1 power, so I'm going to keep it there. M to the 7 power is also happy because it's got a positive power, so I'm going to keep it in the denominator. Okay, I hope this is helping you to understand how this property works. It's a very, very important property. Okay, so properties of radical expressions, these are also very important. Basically, it's very helpful if you can think of a radical expression as an expression with fractional exponent. What do I mean by that? So suppose you take this one, right? If you train your mind and eyes to think of that, any radical expression, as an expression with a fractional exponent. So I can write this b as, that's a fractional exponent, a to 1 over n. So the radical expression is gone. Instead, I have fractional exponent, right? Where is the 1 coming from? 1 is the power of a on the inside. There's no power, right? So it's 1. And the n is the index of this radical expression. As you know, by mathematical convention, if n is 2, we usually don't write it. In introductory algebra books, they write it. But usually, when that index number n is missing, it means that we are taking the square root. If it's any number other than 2, 3, 4, 5, so on and so forth, we have to write it. Then we have no choice but to write that number as the index, and it's called the index of the radical expression. So the power on the inside divided by the index becomes the fractional exponent that we have. So we can go back and forth between an expression that has a fractional exponent to the radical form, or from radical form to an expression that has rational exponent. Okay? So here, what this is saying that if you have two terms being multiplied under a radical expression, you can split that expression into two terms, each one with nth root of one of those terms times nth root of the other. In other words, this multiplication can be split. More importantly, the most often application of this formula is in this direction. It's in this direction. Okay, so oftentimes you have two radical expressions that have the same index. So a square root of something multiplied by a square root of something. Fourth root of something multiplied by fourth root of something else. If the indices are the same, if the roots are the same, then you can multiply it on the inside. So can you multiply? So for example, let's do an example here. If you have, say, cube root of 5 times cube root of, so that's an example, cube root of x, what you can do is write cube root of 5x. You can combine the insides, multiply them, if the index or the root is the same. Now, if this was 3, that was 8, or this was 5, this was 2. Could you do this? No. You could not do this if the indices were different numbers. You can only use this property if that n is the same number for both. The same thing if you have a fraction. If you have an nth root of some fractional expression, you can split that into two, into the numerator and denominator term. So nth root of the numerator divided by the nth root of the denominator. If you have this kind of thing, this kind of expression, in fact, when I was preparing my lecture for the trigonometry class, pre-calculus 2, there was an expression or an example like that. So you can easily then multiply the indices to obtain the index of the resultant radical expression. And by the same token, if you want, you can rewrite this in terms of a fractional exponent. So a to 1 over mn, right? The power 1, which is the power of a on the inside, divided by the index, which is m times n. Okay? This one, then if you've been following all this, then this would be an easy thing, easy property to really understand quickly, right? Because a to n power, nth root of a to n can be written as a to n over n power. But what is n over n? It's 1. So a to the first power is a, which is what you have there. Again, it's extremely helpful if you can train your mind and eyes to think of a radical expression as an expression with a rational exponent. If you can train your mind and eyes like that, you'll get this. These properties will be very, very useful to you. Then the absolute value of a is equal to nth root of a to n power. And that's true for any, let's see, so the n, I should have mentioned here, n should be, a should be positive. So a is greater than or equal to 0. Okay? Because if a is negative, then this index has to be an odd number. Otherwise, we get a complex number, which is not the subject of this. Okay? So if only for a values positive, a greater than or equal to 0, this is true. Okay, so then nth root of a, this is the same thing I was saying earlier, that this small property is so important. All of them are important, but some of them more than the other ones. So this is just saying you can rewrite any radical expression in terms of a rational exponent, or vice versa. You can rewrite any rational exponent in terms of a radical expression. And this one is another property that is very, very similar to that. So nth root of a to m power is equal to a to m over n power. The number on the inside, the power on the inside, divided by the index, which is n in this case. Okay, so let's go over some examples. to see how all of this can be applied to specific examples. So here we want to apply the properties of exponents and radicals, the ones we just looked at, to combine exponents or write radicals in terms of rational exponents and vice versa. So if we are given a radical expression like this, we want to use these properties to write this in terms of a rational exponent. And if we are given a rational exponent, then we want to write it the other. So if we are given something like this with a rational exponent, we want to write it the other way in terms of a radical expression. Okay, what else? Let me rewrite this again. Reread this. Apply the properties of exponent. Combine exponents, and also we have to combine exponents. So all of this goes without saying. So if you have an expression with, say, x to different powers, you want to combine all those x terms into one term. It just simplifies your expression, and you'll be able to simplify the expression and work with it much easier. Okay, so here, so we're not going to worry about what that number is eventually. We're just going to apply the rules of exponent or properties of exponents. So the base is the same, right? 4 to 5th power times 4 to 7th power. So the rule we saw on the previous page was that you can add the powers. So 4 to 7 plus 5 and 4 to 12th power. Okay, so we're just applying the properties. I'm not going to calculate this with my calculator, what that number exactly is, because we're just practicing with applying these rules that we just looked at. So here we have a fraction. The base 4 is the same for in the numerator and the denominator. So we can then subtract. So 5 minus 2 and 4 cubed. As we go through this, please pause the video, write down your own solution, then look at my solution. And then if you have any questions after you see my solution, please look back at this first page where you have all these properties, just to make sure you are following which properties we are applying and when. Okay. This one. So this one is written in radical expression form. We want to rewrite it in fractional exponent form, right? So this is, what's the power on the inside? It is 1. And the index of the radical, or the root, is 3. So we say 6 to 1 over 3 power, like that. Okay. This one, another radical expression. Let's write it in terms of rational exponent. So 6 to 2 over 2 power, but 2 over 2 power is 1, which means 6. All right. 24 to 1 over 2 power. So let's write this in terms of a radical expression. So square root of, the denominator is 2. So this is the square root of 24. And the power on the inside is 1. The index is missing, which means it's 2. So, can we simplify this? Absolutely, because 24 is a product of 2 squared times 6, right? But then 2 squared is being multiplied by 6, not added or subtracted, multiplied. So we can bring it out and put 2 in front. In the process, this power, because it's equal to the index, which is 2, get canceled together. So we have 2 square root of 6. Okay? And that's an equality sign like that. Okay, so we have this term. Let's write this in terms of a rational exponent. So 6 to 2 over 5 power. The power on the inside divided by the index, 2 over 5. Let's do the same thing here. We have 7. The power on the inside is 7. The index is 8. So the power on the inside divided by the index value, right? So we can always go from radical form to rational exponent form, or from the rational exponent form back to the radical form. This one, well, this is just applying properties of exponent. Notice there is no parentheses around -2. So this squared applies only to 2, not to the negative. So we're going to get -4. But if you had, but for -2 squared, if you put the -2 in parentheses squared, then you're going to have +4. Okay, I hope you can see the difference and the distinctions between when the negative stays and when the negative doesn't. Okay, negative raised to any even power drops out. So if this 2 is 4, 6, 8, 10 on the power on the outside, this negative will go away. If it's an odd number, it stays. So if it's 1, 3, 5, 7, if this power is odd, like 1, 3, 5, 7, 9, 11, and so on, this negative stays. It does not get canceled out. But here, the 2, because there's no parentheses, the 2 applies only to the 2. The power applies only to 2, not to the negative. Okay, I had it, I just saw it. I had it here. So this is 4, equal to 4. Here, we have, so let's simplify this. 1/2 to the 4th power is 1/2 to 4th power, right? The power on the outside can distribute itself to the individual, to the numerator and the denominator if they're being divided. Okay, we could not do this if we had terms on the inside that were being subtracted or added. So that times -2 squared is 4. So let me bring up here and simplify. 1/2 to the 4th is 1/16. And then times 4. So 4/16 simplifies to 1/4. Okay. Here, the bases are the same, the powers are different. So we can add the powers because the bases are the same. So 3 plus -1. 3 minus 1 is 2. So 6 squared or 36. This is a fraction involving numerator and the denominator that have a similar base raised to a different power. So we can subtract the power, 5 minus the power in the denominator. Notice, I have an example like that here, so I'll talk about it when I get to m. But this is 10 cubed or 1,000. Okay. So this one, the bases are the same, 3 and 3, but the power in the denominator is negative. So it's the same thing as that, but here you got to be careful because -2 will make this positive. So what this is 3. This power is 1, right? That's that power, 1. Minus, this power is -2. So we have 1 minus -2 is +2. 1 plus 2 is 3. So 3 cubed or 27. I hope this is making sense. So here, how easy is this, right? 4 divided by 4. So write the radical in terms of rational exponents and 10 to the 1st power, which is 10. Okay, so let's start with this one. Here in the properties, we learned that if you have a rational expression raised to a negative power, you can simply flip that, and that will make the outside power positive. So this is equal to -5/4 to +3 power. Okay, and then furthermore, we could distribute this into this. So we could say -5 cubed divided by 4 cubed. And I'm going to leave it like that. I'm going to leave it like that. Normally I would obtain the numbers and simplify the numbers if possible, but I'm leaving it like that because we're just applying the properties we learned. Okay? If you wanted to simplify that, you could. You could do this. You could say, so we could say 5 cubed is 125, right? So that one is easy. So we could just say minus 125 divided by 4 cubed, and that would be 64. And these two, do they have any factors in common? Definitely, probably not. Let's see. So 125 divided by 3. Nope. 164 divided. So it doesn't look like that these can be simplified any more than that. So at least I'm not seeing any those two having this common factors. That's an even number and that's an odd number. Okay. So this one, the same story. We do not like, in mathematics, we do not like a negative power. We want to get rid of it. Now, this is a fraction, so we can flip the inside, 2 over 5, to positive second power, right? That's all we have to do. Flip the inside, and the power on the outside automatically changes to positive. Okay, so here, 1/2 to the 4th, that would be 1 over 2 to the 4th power, right? Distributing this power into the term inside the parentheses. And then here we have a negative power again. So let me flip this and make that positive first. So 2 over 5 to second power. Now let's distribute the 2 into this. So we have the first expression is 1 over 16. That's 1 over 2 to the 4th is 1 over 16. Times 2 squared is 4. 5 squared is 25. Can we simplify this? Absolutely. The 4 cancels with the factor 4 of 16. Here we end up with 4. Right? So 1 times 1 is 1. 4 times 25 is 100. So we end up with 1 over 100. Okay. So let's move here. This one is an easy one, right? This one. We have square root of 81 over 100. One of the properties we saw on the previous page is that we can split this to square root of 81 over square root of 100. So square root of 81 is 9, square root of 100 is 10. Right? So 9 over 10. This one. Square root of fourth root of 81. Whenever you have the nth root of something, see if you can rewrite what's inside the radical or the radicand. If you can rewrite the radicand in terms of an exponent that is equal to the index, in this case 4. So fortunately, in this case, we can write 81 as 3 to the 4th power. So now that power is equal to the index. Remember, we can rewrite them as rational exponents, right? So 3 to 4 over 4 power, 3 to 1st power, or 3. Okay. So do you see why now every time you have the nth root of something, you want to write anything that's in the radicand in terms of a power that is equal to the index? Because if it is, you can bring it out of the radical and you won't need the radical expression. I mean, compare this expression with 3. Would you rather have that in front of you on paper or 3? Of course, this one, right? It's much simpler to work with than 4th root of 81. And here, so we learned that if the indices are the same, which are the same in this case is 2, 2, square root, we can multiply the insides and combine the two radicals into 1. So square root of 36, that's 3 times 12. but we know that square root of 636 can be written as square root of 6 squared. Now, that's equal to the root, right? Or the index of this root. So we can write 6 to 2 over 2 power, 6 to 1 power 1, or 6. I hope this is making sense. Now this one. Okay, so we can split. One of the properties we learned said that we could split a single radical expression into two if it helps us simplify the expression, of course. If not, we'll leave it at the way it is. So square root of 63, we can write it as square root of 9 times square root of, you guessed it, 7, right? Divided by square root of 7. Now this one and this one cancel out. Why? Because they're being multiplied. I've seen this, some people extend this to addition and subtraction. I've seen it so many times. Let me make this clear. Guys, if we have square root of 9 plus square root of 7 over square root of 7, you cannot cancel this. You cannot cancel this square root of 7 with this. Why? Because it's being added in the numerator with this. You must, if you want to cancel this with this, it must be in the, so this is, what is this equal to? It's equal to square root of 9 plus square root of 7 over square root of 7. It's equal to itself. But if you have square root of 9 times square root of 7, just like what we have here, then you can cancel these things out because these two are being multiplied, not added or subtracted. If you had minus here, you would end up with this. You could still not cancel this square root of 7. If you had a minus here, you still could not cancel this square root of 7 with this square root of 7. You can only cancel terms only if they're being multiplied. And then, so we get, which is what in the case we have here, so that's equal to square root of 9. Is this clear? If not, please let me know. Ask questions about it, okay? This course is for you. So you need to get answers to your questions. Don't hold them back. If you hold your questions back, that'll hold you back. So ask away, make sure you understand the material so you can do well in future math courses. Okay, this one here. So we have 4th root of 40 times 4th root of 250. Well, the indices of these roots are the same. They're 4. So we can multiply what's inside the radicand. So this is 4th root of 40 times 250. We end up with 4th root of, this 40 times 250 is 10,000. I know because I've done this example many times. So, and then this is equal to 4th root of 10 to 4th power, and that is equal to 10, right? Because 4 over 4 is 1, which is 10 to 1st power is 10. Okay? And if you have any, let me not skip a step here. So this would be 10 to 4 over 4 power, or 10 to 1st power, which leads to that. Okay? Okay. In these series of examples, we have more but different types of examples, right? So it says simplify the following expressions. So 98. Notice 162 and 98 are both the radicands of a square root. So if I can write any part of these two terms to 2nd power, then I'll be able to remove that term and put it in front. Okay? So let's see. 98, if I... so what can we have that has a factor, a squared factor? So 98 divided by 4. Let me see if that will work. Because if it does, then 2 squared is a squared term. But I'm trying to find factors of that. Okay. Actually, 6 times 16, yeah, 6 times, no, sorry. So 98 divided by 4, nope, it won't work. 98, what other factors are there? 98 divided by 16, it shouldn't work, no. And 98, so let's see, 6 should work. 98 divided by 6, no, it doesn't. So 98 divided by 2, let me go, oh, wow, look at that. So 98 divided by 2 gives us 49, or 7 squared is 49, right? So that's great. So let's do that. We can rewrite the first one in terms of 2 times 7 squared, right? Because I just showed on the calculator that 98 is equal to 2 times 49. And 49 can be written as a perfect square term, which is what we like because this is a square root. And then plus, how about this? This is easier. So 162, we can write that as 2 times 81, right? 2 times 81, or 2 times 7 squared plus square root of 2 times 9 squared. So we want to try to rewrite the inside of these radical expressions to some value to the second power, because now we can simplify things. So this 7 squared can leave. In the process, it loses the power because 2 over 2 is 1, right? So we get 7 square root of 2. The 7 left and lost the power because it's equal to the index. So it's 2 divided by 2 is 1. And that's the power for 7, which we don't write. Plus, the same thing happens to 9 squared, right? Square root of 2 times 9 squared, 9 can leave. In the process, loses the power, times square root of 2. So now we have 7 square root of 2 plus 9 square root of 2. So square root of 2, square root of 2 are the same thing, so we can add the coefficients. It's like 7x plus 9x. What would you get? 16x, right? So this is no different. So 16 square root of 2. Okay, this here, let's do the same thing. 50 is easy, right? We can rewrite it as 2 square root of 2 times 25. 128, let's see. We can write that in terms of, so 40, let's see, 60, 64. So 2 times 64. So 2 times 64, right? So now we can rewrite the 25 and 64 as perfect squares. We like that because this is a square root. So anything to second power can leave the radicand. So we have 2 square root of 2 times 5 squared plus square root of 2 times 8 squared equals 5 square root of 2 plus 8 square root of 2. So we have, this is like 5x plus 8x, right? Because square root of 2 is the same thing. So we can treat this as 5x plus 8x. If this was square root of 5, no, we couldn't do that. We would have to keep them separate. But because the square root of 2 is the same, so we can add the coefficients and say 13 square root of 2. Okay. So this one is really easy because the bases are the same, the powers are different, and we know we can add the powers. 5 plus 9, so we get x to 14th power. This one, once again, that's also very easy. 3 times 4, 12, right? 3 and 4 don't have any powers, so we can just multiply them and not worry about any powers. Y, however, is the same, the base is the same, and 2 and 8 are different. So we can add their powers. So we get 12 times y to 10th power. Remember, if the power is on the outside, like this, we multiply it by the power on the inside. But if there's no power on the outside, then anything that has the same base, we add the powers. Okay, this one, the bases are the same, right? X and X. So that means we're going to add the powers. Like that, right? Are you going to leave this expression like that? You shouldn't. We do not like to keep negative powers. So how could we get rid of the negative power? Remember, we can just, because the denominator here is 1, just flip it. And the power, bring the term with the negative power down to the denominator and make the power positive. So 1 over x2, 4th power. Okay. This example. We have a power on the outside. What do? We distribute it to the powers on the inside. Could we do that if we had that? If we had a to the 4th plus a to the a squared cubed, could we say this? Could we distribute this power to these? No. I've seen this error so many times. Please don't do that. You cannot distribute the outside power to these two terms because these two terms are being added. The same thing is with subtraction. You cannot distribute the power on the outside if you have addition and subtraction on the inside. You can only do this because we have multiplication here, or if you had division like that, the next example is like that, you could do it. You could distribute this power to these, but not when you have addition or subtraction. So please don't commit that error. So distributing, we have 3 times 4, 12, and then a times 3 times 2, 6, right? Then we have, this is the same base raised to different powers, so a2, 18th power. Could you have added these two powers on the inside and then multiplied it by 3? Absolutely. You would get the same thing. So that would probably be even better. Okay, so you could do it like that. You could show a second solution for this problem and say a to 4 plus 2 power cubed. So we have a to the 6th power cubed, or then multiply a to the 18th. The result is the same. Okay, now here, the power on the outside can distribute itself to these two terms because they're being divided. So we have a to 12 power over 4 cubed. Because right now here the power of 4 is 1. 3 times 1, 3. Okay, so we want to, so let's simplify this a little bit because these numbers are not terribly big. So a to 12 power divided by 64. Like that. Okay. Okay, here. So we have z raised to powers on the inside and outside. So let's take this step by step and simplify this. The first one, 3z squared, let's just distribute the 2 into these two terms because they're being multiplied. So we're allowed to do that. So 3 squared times z squared. So notice what I did. All I did was I have not simplified anything because I don't want to combine two things into one for now. I'm going to take it step by step. That way I will minimize my possibility of making an error, right? Like that. So now let's distribute this minus 3 into both terms on the inside. So we have 6 to minus 3 power times z to minus 9 power, right? Are you going to leave it like this? You shouldn't, because you have negative powers and you have 3 squared, which you need to simplify anyway. Okay, so notice right now, it's not on the page, but the denominator of this expression is 1, right? So anything with negative power, you can send to the denominator and make the power positive. In other words, you could do this. You could say, so 3 squared is 9, right? So 9z squared. I'm keeping those because they have positive powers. I'm keeping them where they are. Now 6 to negative 3 power, I'm going to send that down to the denominator. So 1 is not going to be by itself anymore. Now we have 6 cubed, right? It was in the numerator. Now it went to the denominator. The power became positive. And z to the 9th, negative 9th, can also go down and become z to positive 9. Okay? Do we want to leave this like this? Absolutely not. Because, first of all, we have 6 cubed. Let's see what 6 cubed is. 6 cubed, 216. Okay? So we have 9z squared over 216 z to the 9th. Now you have z squared and z to the 9th power. Do you want to leave them like that separate? Both powers are to the same base. So we need to combine this. Now which way you would move the z terms? Would you move this z to the 9th power up? Or would you move z squared down? Think about it before I say anything. Which one would you do? And why would you do that? Have you thought about it? Have you made up your mind about which way you would go? Well, I hope you answered that you'll move z squared down to the denominator. The reason is, if you move z to the 9th up, the power will be negative. And if you add it to 2, you get minus z to minus 7. And then you got to move it again down to make the power positive. So eventually you'll end up with the same answer if you do things correctly. But this way of moving z squared down will reduce the amount of work we have to do to get the final result. So I'm going to move z squared down. So we'll have 9 over 216 z to the 9th times z to minus 2. Right? I moved it down, so the 2 is now negative. But that's not a problem because we can now, z and z are the same bases. We can add the powers. So we can write use this. We can write 9 over 216 z 9 plus minus 2. Right? We can add the powers. So that'll be 9 over 216 z to positive 7. Do 9 and 216 have any factors in common? Let's see. 216 divided by 3. Oh, they do. 72. Right? So we can simplify. 9 turns into 1 and 216 becomes 24 because I just figured out that 216 had a factor of 3, that I figured that 9 would also be a factor, and that guess turned out to be correct. So then we end up with 24. So the final answer for this case is 1 over 24 z to the 7th, like that. That's a 1. 1 divided by 24 times z to the 7. Okay, that's a fraction line. I hope that's clear there. Let me make sure that that's clear. So 1 divided by 24 z to 7. There. Okay, it got a little bit too crowded in that corner. Okay, so let's handle this case. We have this parenthesis that has a power on the outside and this one that doesn't. So for now, let's write this down as it is. So 2 times x to the 5th power y cubed. Now we're going to distribute this 4 into all the terms on the inside because all the terms on the inside are being multiplied by each other. So we can distribute the power that is outside. So we have 3 to the 4th power, 2 times 4, x to the 8th power, y to the 4th power, that's y to 16th power. So 2 times, that's 3 to the 4th, is 27. No, sorry, 81, right? So let me take this step by step. We have 2. Then we have x to the 5th power times x to the 8th power. So x and then 5 plus 8, right? Adding the powers. For the y terms, the bases are the same and the powers are 3 and 16. 3 plus 16 power. And of course times 3 to the 4th, which is, by the way, this piece is 81. Okay, so let's finalize this. 2 times 81, 162, times x to 13 power, y to 19 power, like that. Okay, all right. Let's see more examples. Here we have a fraction, and of course we have y and z in the numerator and the denominator. So let's simplify because we need to combine these like terms, right? So 6 over 2, first of all, that is 3, right? 6 divided by 2 is 3. So 3. Then, for the y terms, would you move y to the 7th down or y to the 4th up? Which way? We need to move them so we can combine them. Well, if you said you're moving y to the 4th up, you're absolutely correct. Because in that direction, you'll have this. Y to the 7th times y to the negative 4, right? I move this up. Now the power changed sign, algebraic sign. Now when you add them, when we add them, we get something positive. Whereas if you moved y to the 7th down, you would have y to the 4th times y to the negative 7. And adding them, you would get negative 3 as the power. So you'd have to move that again. Okay, so this way it's anticipating which way the power will be added to a positive number, helps us reduce the work that we have to do to get the final answer. So with z, what would you do? Would you move this one down or z cubed up? Well, if you answered you would move this one down, you're absolutely correct, right? So let's do that. z cubed times z to negative 1 power. Okay, it had a positive 1 power up there. I moved it to the denominator, and now it has a negative 1 power. So that is equal to, now let's combine things. So 3 times y, 7 plus negative 4 divided by z2 3 plus negative 1 power. So 3, let's combine this, 7 minus 4 cubed. So 3 times y cubed divided by z2, what power? 3 minus 1 squared. Like that. So compare this with this. All the z terms are combined, all the y terms are combined, and the constants are now combined into 1 as well, because 2 was a factor of 6. Okay, this one. Look at this. We have outside powers for numerator and the denominator. I hope you're pausing on each of these examples. I hope you're pausing the video, writing on a piece of scratch paper your solution, then coming back to the video and comparing your solution with mine. If you're doing that, you will win, and you will win big in this course. But if you're just watching the video without writing any of your own solutions down, that's not going to be very fruitful to you. So please, this is just the second lesson in the course. It's way, way too early. You can change that habit, solve problems on your own. Once you have your own solution, then come back to the video. Okay? It's just a pausing and unpausing the video. It's that easy. But the benefits to you of pausing the video, writing down your own solutions, then looking at my solution are enormous. If you take that, if you do that, that's going to be very, very fruitful for you. So I hope now you've done that. You paused the video, you wrote down your own solution, and now you're back. Okay, so let's see what the answer is together here. So I'm going to distribute the 4 into all these terms because all these terms are being multiplied by each other. So I can do that. So x to the 4th, 4 times 2, y to the 8th, 4 times 3, z to the 12th power. In the denominator, 3 times 2, we get x to the 6th power. 3 times 2, we get y to the 6th power. 3 times 1, because z's power here in the denominator is 1. So 3 times 1 is 3. Okay, so now we have x, y, z in both the numerator and the denominator, right? So we need to combine these. And to do that, we're going to have to move things around. So starting with x, which way you would move the x terms? Would you move x to the 4th down or x to the 6th up? Well, if you said you would move x to the 4th down, you're absolutely correct. Because in doing so, watch what happens. You end up with x to the 6th times x to the minus 4. In the next step, we're going to add the powers, and 6 minus 4 is 2, positive 2, which is what we want, a positive power. So with respect to y's, which way you would move the y terms? Would you move y to the 8th down or y to the 6th up? If you said y to the 6th up, you're absolutely correct. So we'd move that, y to the 8th times y to the minus 6. And then, so we'll simplify in a second, right? And with respect to z terms, which way you would move? Would you move z to the 12th down or z cubed up? If you said z cubed up, you're absolutely correct. So let's do that. We're going to do z to the 12th power stays where it was, and z cubed will move up, and it becomes negative power, a negative 3 power in the process. Okay, so let's simplify. Y to the 8th plus 8 plus negative 6, combining the powers, right? They get added because the bases are the same. Then z to 12 plus minus 3 divided by x to 6 power plus minus 4, right? One last step. Y, 8 minus 6 is 2. Z to 12 minus 3 is 9. Divided by 6 minus 4 is 2. So here is our final answer. Compare this, the much simplified form, with the original one that we started with, right? So this is a much better expression to work with than that one. Okay, so this one, we have constants, 8 over 4. Right away, that's 2, right? 8 over 4 is 2. I'm going to write it over there. With respect to a terms, would you move a to the 5th down or a to the negative 7 up? You would, if you said you would move a to the negative 7 up, you're absolutely correct, because ultimately that will help you to achieve a positive power. So like that. How about b terms? Would you move b cubed up or b to the negative 8 down? If you said move b to the negative 8 power down, you're absolutely correct. So b cubed stays where it was, times b to positive 8. Okay, so 2 is 2. We have a, the bases are the same, so let's add the powers. 5 plus 7 divided by, the bases are the same, so let's add the powers. Oops, like that. And so we have 2 times a to 12th power divided by b to 11th power. Like that. Okay. So this one. What did we learn about fractions that are raised to an outside negative power? We learned that all we have to do is flip the inside with no change in powers or terms, just flip everything without any change to powers, and that power is going to be positive. In other words, so flipping that would be 2x to negative 4. Notice I didn't change this negative 4 to positive 4, because the impact of this flipping like that is that it'll make the outside power positive. Okay, so when you, I know this might be a little bit confusing, but it shouldn't be, because these are different situations. See here, when we move things around, it was not in the context of an outside power. There was no outside power there, right? Here, even here, the powers on the outside were positive. We distributed them, and then we played with these terms up and down. But there is a negative outside power here. To make that positive, we flip everything on the inside with no change to powers of or these anything. Just put whatever you see in the denominator in the numerator, whatever in the numerator in the denominator, because we have a negative outside power. So that's why this negative 4, 2x negative 4, when I move the x negative to the negative 4 up, it stayed negative because the effect of this is to the outside power, not to the inside power. Okay, so now we can distribute and do what we did here in these previous examples. So with outside powers that are negative, you should flip things. If you have anything to negative power, you should flip things without, which would make this power on the outside positive, but it would not yet make the inside power positive. Okay, and that's fine. So now let's distribute the 3. Everything is being multiplied or divided on the inside, so we can distribute the 3. So we have 2 cubed times x2 minus 12 power divided by y cubed, right? So let's simplify. 2 cubed is 8. X to the negative 12 power, it's obvious. We wanted this positive, so we need to move it down. So x to the 12th power. Y cubed is happy because it's got a power that is positive. So we're going to write it like that. Okay. So remember, please, if you have an outside power that is negative, when you flip the terms on the inside, don't change the negative to positive or positive power to negative. It doesn't work like that. Move things exactly as they are, flip them exactly as they are, just make the outside power positive. Then go from there. Then distribute and simplify, just like what I did. Okay, so here, 7 is the only constant, so and it's got a positive power, so we keep it there, 7 in the numerator. The x terms, one has negative, the other one positive. Which way you would move these? Would you move the x to the negative 2 power up or x squared down? If you said you would move the negative 2 up, you're absolutely correct. So you have x squared times x squared. So this x to minus 2 power moved up and became positive. How about y terms? Would you move y to negative 3 power down or y to negative 5 power up? If you said you would move the y to the negative 5 power up, you're absolutely correct. So let me keep y to the negative 3 power where it is. I'm going to move the y to the negative 5 power up, so it'll be positive now, right? As we move up and down, their powers change algebraic sign. And the denominator is 1, so we have no more denominators in this case. That's nice. So it came out of being a fraction. So now let's combine these. 7 times x. X and x are the same. The powers are different. So we can add the powers because these two are being multiplied by each other. With y terms, the bases are the same. They're both y's. Now let's add the powers. Negative 3 plus 5. So 7 times x to the 4th power, just add those powers, y to 2nd power, or y squared. So compare that expression with what we started with, right? So that's why it's so important for us to simplify, be able to simplify expressions using those properties. I mean, something that should have been obvious, I'm using all those properties, which means I'm remembering those. Of course, I've taught this course for a very, very long time, and I've been using these properties for a very, very long time. But if you, with a little bit of effort, you too should be able to remember all these things. You are far younger than I am. Your memory works a lot better than I do. So you should be able to remember these properties. With a few examples and exercises, you should be able to remember them easily. Okay, so let's do more examples, right? We all enjoy that because we learn more about this process, applying these properties, and it'll help us understand these examples better. So another negative outside power where we have a fraction. So please pause the video, carry out the simplification on your own. When you're done, come back to the video and see how I've done it. So I'm assuming you've done that, and now you're back. Great. So the first thing I will do is I could distribute the negative 2 power like this. You could do that. That's another possible approach to this. But I want to demonstrate when you have a negative power on the outside, how it works to make that power positive. So you would flip things. So a cubed b to negative 2 power divided by 2 times a to negative 1 power b to 2nd power, right? Notice the only thing I did was flip things. I didn't mess with powers here. The powers stayed what they were, and they should, but the outside power should become positive as you flip things on the inside. Now I'm going to distribute this power, positive power, to terms on the inside. We can do this because everything is being multiplied or divided inside the parentheses. If you had any addition or subtraction between these terms, you could not distribute the 2 anymore. Okay, at least you couldn't distribute it to the numerator or denominator where you had a subtraction or addition. You could still distribute it to the piece that is all multiplied. Okay, so we have a to the 6, 2 times 3, 6, b to minus 4, divided by 2 squared, right? Right now 2 has a power 1. 1 times 2 is 2. 2 times minus 1, so a2 minus 2 power, and b2 2 power, right? Because b has a power 1 before multiplying by 2. Okay, so now look at this. We have a in the numerator and denominator. We need to combine those, and we need to combine them in the direction in which it is going to give us a positive power. Okay, so, and 2 squared is the only constant we have, and it has a positive power. So we're going to leave that in the denominator. So 4 is here in the denominator. A to the 6, a to the negative 2. Which one would you move? Would you move a to the 6 down or a to the negative 2 up? If you said a to the negative 2 up, you're absolutely correct. So a to the 6 times a squared. As a to the negative 2 power moved up, we ended up with a positive 2 power. Now, with respect to b terms, would you move b squared up or b to the negative 4 down? Well, if you said move b to the negative 4 down, you're absolutely correct. So b squared times b to positive 4. Okay, so a to the 6 times a squared, we get 6, we add the powers, right? Because the bases are the same thing, a. I should write this with a different color because things are getting mixed up here like that. So, and then 4, b squared times b to the 4th, so add the powers like that. So we have a to the 8th power divided by 4b to the 6th power, right? So this is what we get after simplifying that. Compare this with this. Which one would you rather have in your, when you work in mathematical terms? This one, right? Not that one. Okay, so we get to rationalizing the denominator. Very, very important. So the way rationalizing works is like this. We multiply the denominator by the root form that would make it a term that is not in radical. So to do that, 1 over square root of 3 should be multiplied by square root of 3 over a square root of 3, right? If you multiply square root of 3 by square root of 3, you're going to get 3. Just plain 3 as a whole number. And that's what you want in the denominator. Some term that is not in any way in radical form. But remember, you got to multiply the numerator by the same thing. It's like common denominators, right? If you want to multiply the denominator of one fraction by a number that would give you the common denominator for that fraction, you got to multiply the numerator by the same number. You can't multiply the denominator by one thing and not do the same thing to the numerator because you'll be changing the fraction. It won't be the original fraction anymore. So here, then, so we have that, and then, of course, square root of 3 over 3. And there's no radical expression in the denominator anymore. Okay, so here, let's use one of the properties we know, which is break this up into square root of 15 over a square root of x, right? That's one of the properties earlier we learned on the first page of this set of lecture notes that we can do, right? That's one of the properties. So now, to get rid of the square root of x in the denominator, we've got to multiply it by square root of x. Why? Well, if you had third root of x, right? If you have third root of x, what would you multiply this by? You would have multiplied it by third root of x squared. Okay? Because you always want to multiply what you have in the denominator by a radical expression so that it would give you a power on the inside that is equal to the index. So if you had third root of x here, you would multiply it by third root of x squared. because third root of x squared times third root of x would give you third root of x cubed, which would mean, again, x can come out of the radical expression. So the reason we're multiplying all these denominators for this one by square root of something, whatever it's in the denominator, it's because they're all square roots. They're all square roots. Look at all these examples. They're all square roots. If I had a fifth root of x, then what should I have multiplied this by? By fifth root of x to the 4. Because then x to the 4 times x to the first power, the powers would get added to x to the fifth power, and then fifth root of x to the fifth power would be x. Okay, so we're multiplying by square root again because these are all square roots. If there were other roots, then we would adjust. Okay, so multiply this by square root of x. We have to do that to the numerator as well. So we end up with square root of 15x in the numerator, which is okay because they want us to rationalize the denominators, not the numerator. Okay, and that over x. Okay. All right, so next, let's, once again, I hope you're pausing the video now. For all of these 4 remaining examples, please pause the video right there. C through F, you have the last 4 problems on the screen. Pause the video, rationalize the denominator for all of these on your own, then come back to the video. Okay? All right, so I'm counting on you that you've done that. You already have your solution in front of you. Okay, so let me then join you. Hopefully my solution agrees with your solution. So we'll break this up into that. Then, in order to rationalize the denominator, we have to multiply it by the square root of 2. But we can't do this and not do the same thing to the numerator. All right? So then, square root of 2x divided by square root of 2 times 2, square root of 2 is 2. Like that. This one. So we can break this up into square root of 5 over square root of 6. To rationalize this, we have to multiply it by the denominator by square root of 6. But of course, we can't do that without doing the same thing to the numerator. So let's multiply that. So what do we end up with? We end up with square root of 30 over 6. Can we simplify that anymore? No, because there's no perfect square factor of 30. If 4 was a factor of 30, yes, we could say 2 squared times something equals 30, and then bring the 2 out and put it in front of the radical expression. But 30, it does not have any perfect square term as a factor. So we'll leave this as it is. Okay. How about this one? So let's break it up into square root of x over square root of 3. And then we have to multiply the denominator by square root of 3 to rationalize it. But we cannot do this without also doing the same thing to the numerator. So we end up with square root of 3x over 3. Like that. And this one, let's break it up into square root of y over square root of 5z. So now, to rationalize the denominator, we have to multiply the denominator by square root of 5z. But we can't do that without doing the same thing, of course, to the numerator. Right? So what do we get in the numerator? We get square root of 5yz, which is fine, because we're not rationalizing the numerator, we're rationalizing the denominator. And here we'll end up with 5z. I hope you're following why this times that gives us that, right? Well, if not, because you're not in the classroom, so I don't know if you have a question about that. But this is how it works. So for this one, square root of 3 times square root of 3 is equal to square root of 3 squared. But this is because this is square root, so this is, you can write this in terms of rational exponents. So 2 divided by 2, so 3 to 1 power, or 3. That's why we get 3 in the denominator. The same thing happens with this, with the denominator here. So square root of 5z times square root of 5z will give us square root of 5z squared. But this is square root of that, so we can write this in terms of rational exponents. 2, this 2 divided by this 2, which by mathematical convention we do not write. This is square root, so this number is 2 divided by 2. So we have 5z to first power, or 5z, which is what you have here. This is the reason why we're multiplying the denominators by what we are. Okay? I hope that, if in case you have questions about that, I hope that clarified it. Okay, we've come to the end of another section here. Thank you for persisting through these videos, and for now, have a very nice day, and I'll see you all next time.